Alright guys, so this proof is really similar to the kite proof in that we got to break it up into parts, and we've got a little bit of work to do in the beginning. So what we're going to start with is we're going to prove that two of these triangles are congruent, and the two triangles we're going to work on are ADC and ABC. So it's this guy here, ABC. ADC is this guy here. Alright, we're going to prove this by side, side, side. So let the diagram be given. Or given a rhombus with two diagonals with the defined vertices and all that stuff, all that good stuff. So first side, we're going to use the given, so AD. Is congruent to AB, and that's given, or by definition of a rhombus. Second side is DC, and that's congruent to BC, and that's by the same reasoning, definition of a rhombus. Third side is going to be this shared side here, AC. So AC is congruent to AC by the reflexive property. Alright, so we've just shown that these two triangles are congruent. By SSS, and therefore we can match up congruent angles. And the angles that we're going to match up are these guys right here. So angle ABE, or ABD, I should say. Sorry, scratch that. We're going to go with show that this triangle is congruent to this triangle, so we're going to go with this guy and this guy. So DAC is congruent to BAC. And again, with the same reasoning as the kite as before, that allows us to use the property of an isosceles triangle. So since now we're looking at DAB, is isosceles, and we just showed that these two angles are congruent, so AE is the bisector. We know a couple different things about AE. Number one, in an isosceles triangle, if you're talking about the vertex angle, which we are, it's going to chop those other two parts in half. So it's going to chop the base in half. So AE bisects DB, which I just marked on here. And we also know that it's going to be an altitude. Alright, so that allows us to say that this is a perpendicular intersection here, so the two diagonals that we have labeled on here are perpendicular. So from that, again, we're going to take the same process as we did before. We're going to define these in terms of Roman numeral 1, 2, 3, and 4, and then just kind of piece together our area. We know that our area is going to be the sum of all of those. So the area of triangle 1 up there is 1/2 the base The base in this case is half of D1. The height is going to be the top portion of D2. So that's this guy right here. So we'll call it AE. And it's the same thing for triangle 2. Alright. Area of triangle 3. Again, is going to be the same as area of triangle 4, but it's 1/2 the base times the height. So 1/2 the base for triangle 3 here. We're going to call that DE, or in other words, 1/2 of D1. And the height is now going to be EC. So 1/2 the base times the height. And again, that's equal to the area of triangle 4 because these are congruent triangles. Alright, the area of the whole thing. That whole thing is a rhombus. It's going to be the sum of these. So we've got 2 of the first one. So area of 1 and area of 2. 2 times 1/2 times 1/2 D1 times AE. That's the first part. And then the second part, again, we've got 2 of those guys. 2 of these. 1/2 times 1/2 D1 times EC. Little manipulation and simplification. 2 times 1/2, that's going to drop off, simplify to 1. So we're left with 1/2 D1 times AE plus, same thing over here, times EC. And again, similar to that kite proof, we can factor out a 1/2 D1 from each one of those. So pull that out in front, and we're left with AE plus EC. Go back up to our diagram. What is AE plus EC? There's AE. There's EC. That makes up the entirety of the second diagonal. So we can simplify this and conclude that the area of any rhombus is equal to 1/2 D1 times D2.